Hello, calculus students, and welcome to another online lesson. I apologize in advance. I feel this one may go a little long. Today we're going to continue our discussion on applications of derivatives, specifically talking about the second derivative, which we sort of began to talk about on the last video, and sign diagrams, which we also mentioned on the last video. We're going to explore those a little bit through the use of about 5 examples. So without further ado, from last class, well, I guess we should first start by talking about what a second derivative is. A second derivative is the derivative of the derivative. So you do a derivative, and then you do the derivative of that. It's the rate of the rate. And we talked about things that they can be used for in terms of displacement, velocity, and acceleration. We abbreviate second derivative as y double prime, or f double prime of x, or d squared y over dx squared. What does that mean? That means it's the derivative, or I'm sorry, the second derivative of y in terms of x. Once again, these things help you with your label. And so what do we have as far as our label goes? You take the y and you put it over whatever the x was squared. So that works well for something like we talked last class, displacement. The derivative is velocity. And that would be like dy dx. Well, your displacement, your x would be like time, and your y would be your distance. That's what displacement is. And so when you go to your label for velocity, it's distance, like miles, and your x is time, like hours, miles per hour. Okay, that's your label for velocity. Now, when it comes to velocity, we do the derivative and we get acceleration. We talked about that last time. And again, our label now is our second derivative, which would be dy. And so y is still time, but then you have the x is squared. So it's y over x squared as far as your label goes. And so it's time, say hours, per second squared. And those of us who are physics students, we know that that is how acceleration is measured, time per second squared. Or another way to say it is like miles per hour, which would be like units per time, but then that's per hour. So acceleration is a rate of time over another time, and that's what we're dealing with here. We talked last class about these last 2 bullet points here. Average rate is asked for, use the slope formula, and when instantaneous rate of change is asked for, use the derivative. All right, moving on. Let's get to an actual second derivative problem. No application here, just a case of second derivative. Giving you a function, f of x equals 2 sine 5x minus 3. And I want you to find f double prime of x. So that is our second derivative. What's the first thing we need to do? Find the first derivative. Little chain rule going on here. We have a 2, which is like a coefficient. As we know, coefficients just hang out. It's still there. Sine of some stuff turns into cosine of that stuff times the derivative of that stuff. The derivative of this stuff here would be 5. We could rewrite that as 10 cosine 5x minus 3. All right, and now we get on to the second derivative. So again, our coefficient just hangs out, so we bring the 10 down. Cosine of some stuff turns into negative sine of some stuff. That stuff stays the same. And then we multiply the derivative of that stuff, which is 5. Clean this all up. I'm going to bring my negative sign out front. So I have negative. I have this 5 and this 10 getting multiplied to become 50. And then everything else was sine of 5x minus 3. Notice 2 derivatives done, and yet my stuff is still the same as when it began, as it's supposed to be, because that's how chain rule works. All right, second derivative, that's the idea. If you can do first derivative, you can also do second derivative. Not much to work on there. All right, more terms of notation. Sign diagram was our second learning intention. Creating them, using them. So a sign diagram is useful for identifying stationary points and increasing or decreasing intervals. Okay, then you might ask, what is a stationary point? Stationary point is a local maximum, a local minimum, and horizontal inflection points. All of these are found when f of x, or I'm sorry, f prime of x equals 0, also known as when the derivative equals 0. So if I have a graph like such, I've got maximums, I've got minimums, or at least local maxes and minimums. It's not the absolute maximum here because the graph continues on above it, but immediately to the right or to the left of this point right here, it is a max, and the same thing for this. So we call those a local max, local minimum, or you could also call them a relative, meaning relative to what's next to them, they're as high as they get. And then horizontal inflection points, which an inflection point is when you switch from curving one direction to another. We'll talk about that a little bit later, but a horizontal inflection point would be something like this, where I'm curving up, and then I get horizontal, and then I still keep going up, but I just switch the direction in which I'm curving. That would also be a stationary point. And by stationary, we mean that the slope is 0. If I drew a tangent line right here, 0. Slope is 0. Draw a tangent line there, 0. And right at this spot right here, it also has a slope of 0. So that's what a stationary point is. Now, what's the point of the sign diagram? Well, again, it's useful for identifying these stationary points, knowing when our graphs are going up and going down. But it allows us to do it without actually having a graph. And I know how much all students love to make graphs. So to be able to find out information about a graph without actually having to make the graph, that is kind of important or cool or useful. So to create a sign diagram, you may want to pause the video right here to write this down. But we find the derivative. Set the derivative equal to 0. Then we plot the zeros on a number line, and by a number line, I literally mean a horizontal line where you just throw the numbers on there in sequential order. And then we put in our plus and minus signs to identify intervals where the answer is either positive or negative. We'll talk about that in a minute. And then we have maximums wherever it has a plus-minus combination, minimums wherever it has a minus-plus, and horizontal inflections wherever we have the same sign twice in a row. So again, you can write those steps down, and then we'll actually see what I mean by all that on the next example or 4. So we've got particle. It moves in a straight line with position relative to some origin O, given by the following function. S of t equals t cubed minus 3t plus 1, where t is the time in seconds. So this is a displacement function. Find the expressions for the particle's velocity and acceleration and draw a sign diagram for each of them. So velocity would be our first derivative. And I know I'm going to be short on space here, so I'm going to start off with a up here. Well, that's going to be s prime of t, which is equal to 3t minus 3. I'm sorry, 3t squared minus 3. And so that would be our velocity equation, which would be in centimeters per second. And then my second derivative would give me my, oh, that's still a, I'm sorry, would still be my, my second derivative would be my acceleration. So s double prime of t. And so I multiply the exponent out front, I get 6t is my whole acceleration problem. Draw sign diagrams for each of them. Okay, so first thing we do is we find the derivative, which I've already done here. Then we set the derivative equal to 0. I'm going to do that in red. So for part A, if I put 0 equals 3t squared minus 3, I can solve this by adding 3 to both sides. 3t squared, divide both sides by 3, and I get t squared equals 1. The square root, remember, if you write the square root sign, there's 2 answers, so this becomes t equals positive or negative 1. So we found our derivative. We set the derivative equal to 0. We now take those answers and we plot them on a number line. Okay, so we had positive 1 and we had negative 1. Obviously, you have to put the negative 1 in front of the positive 1. Other than that, I don't care about the scale. So just any old number line, you throw the numbers on there. Now, we check values in between there, or in those different ranges. Obviously, if you plug a negative 1 into our derivative function right over here, this derivative function. Plug a -1 in, I'm supposed to get a 0. I just checked that right here. Solve for 0. If I plug a 1 in, again, I should get a 0. So these are the spots where I either have a maximum, a minimum, or a horizontal inflection. That was the whole point of doing this. Now I just want to know which one it is by knowing what happens after those spots. So my graph going up, going down, things like that. So anything before -1 should be going in a certain direction. So let's check a number like -2. So I go back to this function here, and I'm going to try s prime of -2. I'm going to plug in a -2. So 3 times -2 squared minus 3. Well, when I do this, I get -2 squared, which is 4. 4 times 3 is 12. 12 minus 3 gives me 9. I don't really care what the number is. I just care that it was positive. Then I know I plug a -1 in, I would get 0. Now about a number between the -1 and the 1 on the number line. Again, where am I getting -1 and 1 from? Right here, -1 and 1. Let's pick a number between there. Well, that's the greatest number of all to plug in, 0. If I plug a 0 into this function, I would have s prime of 0, which equals 3 times 0, which is 0, minus 3, which is negative. So in between here, I get negative values. Let me get that in a better color. So negative values in between -1 and 1. And then last but not least, do a number greater than 1. I plug something in for that. So s prime of, well, let's try 2. You could also do 10, 5, any number that you want to plug in, but I'm going to do 2, some number greater than 1. I have 3 times 2, which gives me 6 minus 3 gives me a positive number. So my sign diagram goes positive, negative, positive. So what does that mean? That means that our derivative here, again, derivative slope or rate, our rates were going up. And then when we got to -1, we flattened out, -1 comma something. And then after -1, we go down until we get to +1. Again, these are x values, not y values, comma something. And then from that point on, we go back up. So we can see by going from positive first to negative second, going up and then down, this -1 must be a relative maximum. And we can see that then going down with our negative and then coming back up, that +1 must be a relative minimum. And I kind of drew the sketch to help you think about it, but you don't have to draw the graph. If you go up and then down, the 0 value or the relative, the local, the stationary point has to be a maximum. And the other one, again, has to be a minimum. So we could do the same thing for our second derivative. Where we set our second derivative equal to 0. We had 6t. I'm going to do my work down here. 6t equals 0. Divide both sides by 6. And so t equals 0. So my second derivative sign diagram is going to look like this. And I have a 0 right here. I check a value. Anything greater than 0, I plug it in. I get a positive value. Like if I plug in 1, I get 6. So anything greater than 0, anything less than it, if I plug in a negative value, 6 times -1, I get a -6. So there. So what does this mean? This means that for this particular function, which is talking about a particle moving, if we go back to our first derivative, this represents velocity. So our velocity was increasing until t equals -1. Then from t equals -1 to t equals +1, it was decreasing, meaning we were slowing down. And then from that point on, it was increasing after t equals 1. No, let's try that again. I said slowing down. That's not what I mean. Negative velocity means you're backing up. That's what I meant to say. So between -1 and 1, we were actually moving backwards. From 1 and beyond, we were moving forwards, and -1 and towards negative infinity, we were moving forwards as well. For this tells us whether we're slowing down or not. And anything before 0, we were slowing down. Anything after 0, we were speeding up. So let's move forward. Part B, find the initial conditions and hence describe the motion at this instant. So the initial conditions are, going back to this original problem, if we can sort of read in there, t is greater than or equal to 0. So our initial condition is 0. If I plug a 0 in, I know that I'm going to be getting a negative value for my velocity, meaning I'm moving backwards. Now we can figure out exactly what that is. We get a negative 3. How did I get that? I plug a 0 into this function. I can do that right here. So 3 times 0 squared minus 3 gives me negative 3. So my velocity was negative 3 centimeters per second, which means I was moving backwards at 3 centimeters per second. Then, what else do we know? We know that I was at 0 for my second derivative. I was transitioning from decreasing to increasing my speed. And so basically from 0 on, I was speeding up. Now, if you're moving backwards and you start speeding up, watch what happens. So I'm going backwards, but it's almost as if I'm slowing down because I'm starting to have a forward momentum. And so it's sort of like if you have a big heavy cart, like if I'm wheeling around one of those cow carts, and you start putting a force against it, eventually the cart's going to keep going backwards, but it's going to slow down until it eventually starts moving forward. And that's what's happening here. So we're quote unquote speeding up, meaning that we have a forward acceleration, but since we were already moving backwards for the next second, we're still going to continue to move backwards. Describe the particle motion at t equals 2 seconds. Well, t equals 2 seconds, we already know from our sign diagram that our velocity is positive and our acceleration continues to be positive. So we're speeding up and we're moving forward at that point. Find the position of the particle when changes in direction occur. Well, our change in direction occurs at t equals 1 second. That's where we moved from going backwards to moving forwards. So t equals 1 second. And then for part E, draw a motion diagram for the particle. I sort of already did that, and due to space and time, I'm not going to continue on with that one. But then finally, after what time intervals is the particle speed increasing? That would be the interval from t is greater than or equal to 0. From 0 on, we are increasing in speed. All right, some graphs going on here, and this might be maybe where we'll end for today's video. Indicate and clearly label on the graph the points where f has minimum points, maximum points, and points of inflection. It should probably be stated that a point of inflection, and I think I actually have this on the next slide, a point of inflection is where your second derivative equals 0. Now, what is a point of inflection? We talked about a horizontal inflection, but the idea is if I'm curving in one direction like this, where I'm just curving, if I kept curving in that direction, I would make a full loop or circle. But if I curve in one direction and then suddenly I decide to turn the other way, like that, like if you're thinking of this as a road and you're looking down, obviously here you'd be turning the wheel to the right to go here. And then right when you get to about this spot, you turn the wheel to the left. What it means is we've had a switch in concavity. Up to this point, we were curving downward, and then we get to that inflection point, and then we start curving up. And you say, I'm still going down right here, but if you were like, for example, in a plane and you were in a nosedive at that point, you then start curving up to make this happen. So this right here would be a point of inflection. And when does it occur? It occurs when the second derivative equals 0. So the diagram is not actually showing the original function. It is showing the derivative of the function. So what does the derivative represent? The derivative represents slopes. So we have, from this spot all the way through here, what kind of outputs do we have? Well, they're negative numbers. So all throughout this area, we have negative slopes. Then throughout all of this region, we have positive slopes. Then more negative slopes, and then more positive slopes. All the other spots that I haven't circled, we have outputs of 0 on this graph. And those are the spots where we have no slope whatsoever. So how is it possible that we start off with a negative slope, and then we have no slope, and then we have positive. Well, what does that mean? So we start off and we're going negative, and then we get to this spot right here, which I'll call A. And right at A, there's no slope. No slope whatsoever, so it has flattened out like such. Then, from that point on, we start going up. We have a positive slope. And the positive slope's getting higher and higher and higher until it gets a little bit less high and less high and less high until it goes back to what I'm going to call point B, where there is no slope at all. And then it has to have a negative slope for a little bit. I'm running out of room here. And then finally, it would hit C right there. And then it has a positive slope from that point on. So that's the overall shape of the graph. So where do we have minimums? We have minimums at what I have labeled A and C. So that would be right here would be a minimum, and right here would be a minimum. And point B on the original graph on f of x is actually going to be a maximum. Again, we can see that here on this sketch. So that was point B. And then last but not least, where do we have inflections? Inflections would occur anytime our slope of our slope is 0, which would be right here and here. So this would be a inflection point, call it IP, and here would also be an IP. Now, where do those correspond on our original graph? They would be in between A and B. So that would be right here where I switch from curving up to curving down, and then halfway in between B and C where I switch from curving down to curving up. We'll finish with these notes and then call it a day on this video. Increasing interval. Our graph is going up anywhere our derivative is greater than 0. Decreasing interval. Our graph is going down or has a negative slope or collection of slopes whenever the derivative is less than 0. Concave downwards. Our curve in which is curving down, or like a parabola that opens down, all of that is concave down. That's wherever our second derivative is less than 0, or our second derivative is negative. And we're concave upwards, which would be like an open parabola. All of this is concave up. That would be wherever our second derivative is greater than 0. And a point of inflection occurs whenever our second derivative equals 0. We already talked about maxes, minimums, and horizontal points of inflection also occur whenever our first derivative equals 0. All right, we'll look at more examples like this. Our last couple examples we'll look at in class next time. And we'll give you some book work to look at in the meantime.
Those students that missed the archery tournament meeting, please meet in the gymnasium
On page 421, number 1 through 6. Until next time.